Thank you. Hello everyone. My name is Olipriya Pramona. I work in Aqua Robotics team as a senior software engineer, and I do AI mostly. So, let's get into today's agenda. I have purposefully eliminated code from today's presentation because it will be yet another tutorial on how to load the models and train the models, and we don't want that actually. So we will talk about how Aqua Robotics is actually working, the process of choosing the model, choosing our problem definition, and how if you presented with a similar kind of problem of training a custom model your own data, how any of us can actually approach it. So I'll basically talk about what is the target of Aqua Robotics, um, how we chose our problem definition, why we decided to train a custom model, and how we chose the right model for us. A little bit about transfer learning, our dataset preparation, I'll talk about some of the experiments we conducted so far and an example scenario where anyone can develop a custom model. So let's dive in. Uh, First, talk about the target of Aqua Robotics. Aqua Robotics is actually a manufacturer of fish cage cleaning robots. So in Norway, salmon farming is a quite profitable business, I guess. There are a lot of companies doing this kind of farming where they have big cages in the ocean for salmon farming, and government is very strict about cleaning these cages. So these cages have to be cleaned all the time, otherwise there are heavy penalties. And doing this manually uh, is expensive. Rather than using a robot is less expensive in this industry. So Aqua Robotics is such a company that manufactures these kinds of robots. And the sole purpose of these robots are cleaning these cages. So far, Aqua Robotics robots are basically mechanical, but they are thinking about uh, incorporating intelligence into them. So right now, they work on a fixed cleaning pattern, or should I say, brushing pattern of cleaning these cages. But their target is to incorporate AI by incorporating cameras onto their robots so they can decide what area needs what kind of cleaning. So all the areas are always clean. Uh, Otherwise, without manual inspection, you do not know how much an area is clean or not clean. So that's the target of Aqua Robotics. Pretty simple. They want to detect fungi growth and detect any potential holes with these cameras. And you can see some example images of high growth and low growth. These are some categories we divided our data into. So we have three growth categories: high growth, low growth, and medium growth. And we will talk about the data in later slides. So this is the initial target of Aquarobic. Now, let's talk about the problem definition. Why I bring this up in particular is when we were getting the client brief initially, they were saying that we want to detect growth and we want to detect holes. And when you hear detection, your mind immediately goes to object detection. Those of you are familiar with such AI tasks, you know that object detection is another um, task, AI task. So when the client is continuously saying that we want to detect growth and detect holes, you might be tempted to use object detection here, but we will not use object detection here. Why? As Object detection
I'm so
actually,
sorry, Oliver, to
yeah,
interrupt. The
yeah,
স্ক্রিনটাকে আরেকটু
sure.
বড় করে ভিউ করা যায়? স্লাইডস যেগুলো ভিউ করছেন, এটা জাস্ট মনে হচ্ছে অল্প একটা পার্ট আসতেছে।
Sorry.
স্ক্রিন শেয়ারিং
Uh,
অপশনটাতে আই ক্যান সি টু স্ক্রিনস, মানে আপনাকেও দেখতে পাচ্ছি, স্লাইডটাও দেখতে পাচ্ছি। এমন যদি
oh,
একটু
oh,
করতেন
oh.
যে খালি স্লাইডটা আরো বড় করে দেখা যায়, তাহলে এটা ইজিয়ার হবে
Okay,
সবার জন্য।
okay, okay. Let me share again. Mm, you can see me?
পারফেক্ট, পারফেক্ট, হ্যাঁ, পারফেক্ট।
Okay.
থ্যাংক ইউ, ইয়া,
Uh,
গ্রেট। সো সরি টু
okay.
ইন্টারাপ্ট, প্লিজ কন্টিনিউ, ইয়া।
Yeah, it's okay. So, yeah, yeah. So, what was I talking about? Okay, I was talking about object detection, and what object detection does, it will detect the growth and also tell you where in that image is location of the growth, the pixel location. And in our case, if you listen to the client brief carefully, you actually do not need the location of the growth because they already saved the location data of that image. So you do not need to tell the client that within that image, where is that growth. And even if you go with like detecting growths and counting the number of how much uh, growth is covered, that's like using a heavy tool for a very small task. So that's why we do not need object detection, at least in growth. And in case of hole detection as well, we might be tempted to use object detection here, but here again, we do not need the location of the hole in particular within that image because the client will say the location metadata of the image. So we just need to know that if that image contains holes or not. It's a simple yes no question. So classification will do. We do not need detection. So that's why I bring up the choosing the problem definition because we have to decide what kind of task we will do. And when we initially got the client brief, it seemed like we need to use object detection, but in reality, we don't. They will divide the cage into different sections and in different zones to be particular. And they need to know that if this zone needs more cleaning or less cleaning. So we can just have each image and say if that has a high growth or low growth. The rest of the thing, the rest of the calculation based on the zone will be done later. So we do not need a particular location within that image for high growth or low growth, anything. So we chose image classification for our task. Um, why we opted for training a custom model. You might have already guessed it's a niche area. We do not have off-the-shelf models working on underwater data, detecting holes or growths. And it's a very domain-specific task, and pre-built AWS models will give you whatever they provide with no control over layers or losses or evaluation metrics, even if you want to train their models with your data. So, training our own model will give us more control with the architecture and all of the functions, the evaluation metrics, and everything. And we opted for a very simple pipeline. Initially, we just had an EC2 instance to train the model and nothing else. We developed the system later, but initially we were training the model on EC2 instance too. So, and another point here was that we had very limited data and it was not predictable at that point that how much data our client will be able to provide us and how we will prepare the data for our task. Do we need to change the problem definition or anything later on? So we decided to have more control on our end. That's why opting for a custom model. So um, here, when I mention about custom model, obviously I'm not talking about reinventing the wheel, right? I will not develop a model architecture on my own. There are a lot of smarter people than me publishing papers every day. So I can just choose models from there. So this is what transfer learning actually means. I'm sure all of you already know, but just revisit it a little bit. Transfer learning is, as you can see from the example here, I need to classify vehicles, car, truck, bicycle, a lot of categories. So if I train from scratch, CNN, it will take a lot of time. It will take a lot of data. But with transfer learning, I can just choose a model that is already trained with, let's say, cats and dogs. I can use that model and train with my new data. It will converge early and it can perform better even rather than training from scratch. And I won't need as much as data with transfer learning. Uh, so that's the benefit of using transfer learning. Like if you are using a model trained on a broader task and then using it on your specific niche task. So when are we using transfer learning? Specifically, when you have minimal data, you don't have the computation capacity to train a model from scratch. Um, and the target data set is actually related to a larger data set. The models are available on the larger data set. You need faster convergence and you want generalization. When we use transfer learning, the model already knows. Let's say I am using a model trained on cats and dogs. The model already knows the uh, how to detect the edges of the images and create a pattern between them. So it's already trained on a broader task, and then I'm using that to detect cars, I mean, classify cars or trucks. So it will be more generalized in that sense. Um, so let's talk about choosing the model. How how do we choose the model? In our case, in my case particularly, at first I considered the task at hand. So I was working on image classification. So I'll go onto a site called Papers with Code. This site is actually unavailable right now. Uh, it was a great site called Papers, searching recent papers. Uh, so I'll go to Papers with Code, and they will have the latest papers on the topic, and they will list out the important parameters published by those papers, and you would be able to sort that, filter that, everything. So I'll go to that site and list out some papers, and then look at my criteria. First criteria would be what kind of hardware is the target infrastructure. So, where will I deploy this model? I'm not deploying this model on a mobile device or anything. So my model doesn't need to be lightweight. Another consideration, even if the hardware is heavy, but let's say I want the model to be fast. But in my case, I didn't need the model to be fast or real time. So that's one of the plus point in my case. Then I'll search for papers that are not much older than 3 years and check if those papers have repos in the is the code available in my preferred framework. I prefer to work on PyTorch. So if that's available, is the code clean enough to use? Um, is the model has a good accuracy with time and parameter constraints? I have mentioned it as a bonus here, but it's also important in transfer learning if the weights are available. Not all the models make the weights available, or not all the reports. So if the weights are available, is also another important consideration when you are using transfer learning. So I'll make a list like this. There were a lot of models in this list actually. I have trimmed it down to show here, but I'll make a list like this, like paper, their photos, and list out their different restrictions I was considering, like the accuracy, the param count. Param count is basically higher the param count, the heavier the model. If the weights are available, inference time means the time it needs to predict one image with that model. So inference time in CPU, inference time in GPU. And these times are sometimes not very accurate when you take the time mentioned in the paper, because they mention with whatever they have tested. Let's say they are testing the image with 230 by 230 pixel image, but you need the model to be 1080 by 1080. So you actually need to test the model yourself and uh, get these numbers yourself sometimes. And is executable is actually, it seems funny here, but initially when we are choosing the models, we do not give time more than 1 day in these repos, as you want to find your model fast. So sometimes the code will not be, we will not be able to execute the code in 1 day somehow. So if it's executable right away, okay. If it's not, we won't waste time on it. So that's how we list a lot of models and go through it, test on our data, some of our images, how much time it takes to inference, and so on. And then we choose a model that fits our criteria. I choose NFSNet for our case. As you see that it's a very heavy model actually, but with high accuracy and comparatively low GPU inference time. And as I had no hardware restriction in my case, I chose a heavy model at that time. So let's talk about dataset preparation. After choosing the model, we moved on to dataset preparation. And in our case, initially client provided only 5,000 images. So think about it, training a model with only 5,000 images. The images were in good quality, mostly well-lit images, 1080 by 1920 pixel. Less than 10% images were shaky. And you can also see the category distribution here of high growth, low growth, and medium growth. High growth being the highest amount of images, but we cannot train our model with these 5,000 images, right? We had to come up with something to uh, actually increase the data. So just a minute. Can you see my screen?
Yeah, we can.
Okay. So for dataset preparation, we actually came up with this idea that we will use crops of images. So as you can see, we will go over the image in a zigzag pattern and take 320 by 320 crops from one image. In this way, we were able to generate 15 to 16 images. from one image. And when we reach the edge of the image and there is not enough uh, image area left for 320 crops, we will just shift the starting point a little bit so that there is overlapping in that area and we get that last bit of data as well. Because as we have so less data, losing even that much was a lot for us. So we created our first dataset one, which had 320 by 320 images. And by this, after a lot of manual sorting and everything, we were able to generate actually 76,344 images. And here I have mentioned a few data sets we have prepared along the way. In dataset 5, we first stratified the dataset, meaning in training and validation, both the category distribution were same. In dataset 6, we first use colored nets. So as you saw the images examples, we got only one colored nets, but our client mentioned that nets could be any color. So to add that variety, we need to use colored nets. But it's not that simple that we will change the color of the image and we will get colored nets, because it was a project in itself, you generating colored nets, because if you change the color or brightness of the whole image, um, the color of the ocean behind it and also the growth will change. And you don't want that. You only want to change the color of the net. So we actually had to create masks to separate the nets from the rest of the images, change the color of the nets, and then stitch back all of it. Uh, and we had to go through it manually again to eliminate any unrealistic images as well. In dataset 8, we started using large images. We stopped using the crops and we started using 1080 by 1920 pixels because ultimately our target is larger images. Our model will predict on larger images. In dataset 9, a client added more data with hexagonal white nets. So this added variety. Um, on dataset 11, we added holes information, which is basically synthetic holes. Client didn't provide us any real data on holes at this point. Uh, and as you can see, we have a variety of versions of dataset, as I've mentioned here, and we didn't prepare this dataset before starting the experiments actually. We probably had first few experiments with dataset one only, then we moved on. So this is a trial and error process that we developed the dataset with our ongoing experiments. So let's move on to the experiments a bit. So first three experiments, the model was not stable. We had some issues with the code and everything. And on experiment four was the first experiment where we were able to train the model as we wanted to. And here we actually wanted to freeze the whole NFS net and add our own, some of our own layers and train that model on our data. What freezing means, the NFSNet, is that during the training, the weights of NFSNet will not update. The weights of only our added layers will be updated. So as we can see on the upper graph of experiment 4, the training loss graph is higher than the validation loss, meaning that um, during training, the model is not capable of learning the patterns in the data properly, which was expected. We didn't expect any better from this experiment. On experiment 5, we started defreezing layers of NFSnet. and we decrease the final convolution layer of InfSNet. And as we can see, the model started learning better. It learned so much that it started overfitting. So overfitting meaning is it's learning too much of our data, almost like it's memorizing the data. And we don't want that either. We want the model to learn just enough to be generalized. So in the next experiment, to battle overfitting, we place something called dropout, which is basically um, dropping some of the model connections to make the model more generalized, and did a bit of hyperparameter tuning to for a good dropout value. And as you can see, it improved from the last experiments, but obviously this is not it. We will go on further with our experiments. On experiment 7, we got new data from the same site, but it was at a different time of the day and it was shot in portrait mode. And this data was vastly different from the original data we got. And we tested our previous model using this data and saw that the model was not performing well. So it actually shows the cracks of our model, that our model is not generalized enough, which is okay, expected. So we prepared dataset 2 with the new data, and we discovered a pattern in our data that it's misclassifying a lot of low growth examples as medium growth and a lot of medium growth examples as low growth, because when we were annotating our data, we might have some overlaps in those categories. So we needed to redefine the whole data set. And at this point, we had 100K images in training. So you can imagine how much data we had to go through manually for conducting these experiments. But as you can see, uh, even after redefining and everything, the model is massively overfitting. So for the next few experiments, we actually battled overfitting and with no improvement in results. So in experiment 14, we actually developed a subset of our data and trained ResNet and EfficientNet V2, which are common uh, image classification models used as building blocks in many things, uh, and train these models for 100 epochs with our subset data to check if there is a problem in our data, that if there is some unlearnable pattern or anything, to check if there's a problem in data. And we can see that these models are converging. So there are no problem in data. So we started the same experiment in our NFS. And to our surprise, that the more layers we freeze, meaning the more layers we didn't train, the more improvement in the results. This is with the subset, by the way, not the original set. So from this experiment, we concluded that for the whole data set, the model is not complicated enough. It's not capable of capturing. The entire data set is way too big for NFSNet when we are only decreasing a few layers, final convolution layer up or a final block. So we need to decrease more layers with our original data. So with this information, we moved on to experiment 15, and here we had two iterations where at first we decreased 5 blocks and then we decreased 6 blocks. And there are subtle differences, but we could see improvement in the test data. But the thing is, when you decrease these layers, you are actually increasing the size of the model. Ultimately, you do not want that. You want a minimal size, but a generalized model with maximal results. So, like refreezing the whole model and training with our data will not work in our case. On experiment 16, we added some runtime augmentation. So augmentation meaning doing some cosmetic changes on the images in runtime. By cosmetic changes, I mean that you flip the images or change the brightness, saturation, or anything during the training. So these augmentations will not actually replicate the real world scenarios. What it will do, it will add complexity to our training set. And it will force the model to learn with high penalty to eliminate the tendency to memorize the examples. And we see the improvement actually on the test data as well. This model performs great. And here, half the blocks, I think six blocks of enhancement are decreased, and we have added some runtime augmentation on top of the augmentations this report already had. So results were improved, but as I already said that we need to minimize the size and also improve the results because this is going to overfit at some point. So in experiment 17, we introduced change in architecture. We already knew at some point we will change the architecture of the model. So at experiment 17, we finally did that. We kept half of the model as it is and freeze. So we can benefit from the transfer learning. The initial layers will do the basic tasks of classification, and the last few layers where we can actually change the architecture and reduce the size. So we change the architecture as such that the model weight can reduce. And we were successful in that. And as you can see from the graph, that the training loss and validation loss has started to align. Um, um, Taking inspiration from the previous experiment, in experiment 18, we actually uh, moved on to the larger images. It is the first model with 1080 by 1080 pixels. So in this experiment, we added some massive architectural changes so that the model accepts the 1080 by 1080 pixel images. And also, we can use transfer learning to our benefit. And as we can see, the loss graph becomes smoother, and the results were actually quite better in this experiment. And from here, we actually improved our experiments further and we added holes. And ultimately, with this model, we did 23 experiments in total, and these were at experiment 23, the results were really aligning and it was better. But after experiment 23, we just decided to move on with another model, another lightweight model, uh, and start the training process from scratch again. So, I didn't show that many experiments here because obviously I'll lose all of you. But what have you seen so far? Let's see if we can apply that knowledge in a similar kind of scenario you might encounter in your project or anything. So, as I have a small baby, I always think about childcare systems in our country. So, I went for a childcare center related example. So, let's say the client is telling you that they want AI to go through the publicly available photos of childcare centers to determine if they are worth investigating further for funds. Uh, Keep in mind, they are not going through the publicly available other information. They are just saying when you Google the images you get, you will go through that images. Originally, someone from their company goes through that images and proposes the center for further investigation, but they want AI to do that to eliminate the effort. So, what will be our first instinct in this case? Uh, if we do not consider about the code or anything, let's just see that first step in this case would be establishing the problem definition from the client brief by getting clarification from uh, what do they mean by eligible for further investigation? What are they actually looking for when they are seeing those pictures? Obviously, there are some criteria. Do they see in that picture if the area is clean enough or anything? So get those information that what are their exact criteria. Do they look for anything in particular? Do they look for any kind of alarm system if that is present in those images or anything? I don't know, but we have to get the brief from the client, so what they are looking for, and from there we can build a system. We can define a problem definition. Let's say they are looking for clean environment, so they have to define for you what are they considering clean and unclean. So you can train a classification model for clean and unclean, or worthy of investigation, not worthy of investigation. Depends on the brief and the clarification you get from the client. Then you will choose the model based on the system requirements they are willing to provide, like in what system they are going to run. If they don't have anything, like in what hardware are they going to give you or anything, then you will have to come up with those as well. But uh, you will ask the client for clarification here as well, and then choose your model based on that. You will start preparing your data and then start fine tuning for your specific task. But the process is not actually linear, it's a trial and error process. I showed the initial experiments that were mostly, we would say, fail, because see, you cannot know from the beginning what these models are going to respond to, what kind of data, to what kind of value. So you will have to make the changes very small and very specific, so you can actually gauge its impact on the model, on your data, and everything. So yeah, that's actually the framework we use, robotics uses, and I personally use when I am training a custom model. So yeah, that's actually all from my side. Do you have any questions that we can answer within the time limit? Probably. So yes, thank you for saying the alternative of papers with code, but I find it not good enough uh, for what it was. Papers were more efficient than uh, hugging face papers with code. So yeah, anything else? So, if anyone has more questions that you cannot think of right now, or the answer you think will be a lot complicated, you can just ping me on Slack and I'll be able to answer. If there's no question, then we can just conclude this session today.